Hi, my name is Jason Provol, and I want to be an engineer when I grow up. I'm a 9th grader at Scripps Ranch High School in San Diego, California. My science fair project is a continuation of a 2013 study. During the summer of 2013, I built a wind tunnel in my garage for quantitative analysis of lift and drag. I learned many key principles relating to aeronautical engineering, which I applied to this year's project. Last summer, Asiana Flight 214 crashed at the San Francisco International Airport. The plane was coming into the runway too low and too slow to complete a safe landing. As a last resort, just before touchdown, the pilot lifted the nose to try and regain altitude. The lifting of the nose of the aircraft created a stall situation. The aircraft lost more altitude and the tail section hit the seawall just before the runway. 2 people were killed and many were injured. Stall occurs when airflow over the wing separates or detaches from the contour of the wing, resulting in a loss of lift. When an airplane is at a high angle of attack, the airflow over the wing does not follow the entire contour of the wing. This results in airflow separation. If this separation could be prevented, the aircraft lift at high angles of attack could be improved and crashes like the Asiana 214 crash could be prevented. As a result of an award I won last year from the American Institute of Aeronautics and Astronautics, I was introduced to Mr. Ricardo Torres, a graduate student at San Diego State University. Mr. Torres and I discussed my objectives and together reached the conclusion that the synthetic jet actuator had great potential. I prepared and submitted a proposal to San Diego State University to perform testing of synthetic jet actuators to improve lift during stall situations. This proposal was accepted, and in the fall of 2013, we initiated testing of the synthetic jet actuator. A synthetic jet actuator is created by inserting a piezoelectric disc into a resonance chamber with an orifice at one edge of the chamber. An oscillating current is introduced to the disc, resulting in pulsating airflow in and out of the orifice at a selected pulsation frequency. If the disc is inserted into the upward surface of the wing, it is hypothesized that energy introduced by the pulsating airflow will disrupt a shear layer formed between the boundary layer and the free-stream flow, which results in an instantaneous reattachment of the airflow, and this improves the lift during the onset of stall. The synthetic jets tested are potentially full scale of the types of devices that would be inserted throughout the surface of a commercial aircraft wing. In preparation for testing at SDSU, I first modified and rebuilt the 2013 home wind tunnel and performed preliminary testing targeted at developing an experimental technique and test plan. This was followed by formal testing at SDSU. I created an airfoil modeled on the NACA 2414 design with the synthetic jet actuators inserted into the surface of these newly manufactured wings in the SDSU machine shop. These airfoils were tested at velocities ranging from 0 to 44.7 meters per second, 100 miles per hour, and angles of attack ranging from 0 to 20 degrees at piezoelectric disc frequencies of 550, 650, and 750 Hz. Over 360,000 data points were collected, including force measurements on 6 axes and particle laser photography of the airflow and air separation. Analysis of the data showed that the synthetic jet actuator improved lift performance by as much as 40% in pre-stall conditions. Applied to a 747 aircraft, this would result in over 40,000 more pounds of vertical lift force in a high angle of attack. This means that as an aircraft approaches stall could be avoided. Alternatively, if this were applied on a 747 aircraft, 40,000 more pounds of cargo could be carried during flight. In conclusion, the synthetic jet actuator is a very applicable and very promising device to avoid stall and to improve airport performance at high angles of attack. Thanks for listening.